Hello everybody, I'm Riccardo Mori, and this will be the talk about Fuzzing and ntopng and how I implemented the fuzzing test for ntopng. So I'm from WhatsApp. I'm a security researcher there in the automated analysis team, where we are doing vulnerability research, and my main focus is on reverse engineering and fuzzing. So, what is the target of this presentation? Basically, we want to identify bugs in the software, and there might be multiple definitions of what a bug is, but in this case, we are just considering it as a misbehavior of the program. So when it deviates from the normal execution. Since finding bugs is a really manual and tedious job, and a lot of the times we are missing them, we want to automatize it as much as possible, and if possible, we want even to integrate it in a CI/CD pipeline, so that we really can have automatic testing at every commit or every release, every time we want. So this is where fuzzing really came into place. It's basically a technique to automatically test software by automatically generating test inputs. And there are various strategies to generate them. It's a concept that came out quite recently. The first mention of the term fuzzing was in 1988. But only in the last 10 to 15 years, there has been like a huge spike in the usage of fuzzing to find vulnerabilities, and we have seen a lot of tools coming out in the last years. How does it work? Basically, the idea is pretty simple. We generate some input, we send it to the software, and then we detect if the software crashes. If it crashes, it means there is a problem, and we can fix it. Otherwise, it's okay. This is really the general approach. In reality, in the literature, there are 3 different categories for which we can generate inputs in different ways. These are called the black box fuzzing approach, gray box, and white box. In black box fuzzing, we have no conception on the internals of the software that we want to analyze. Basically, we treat it as a pure black box input-output machine. We just generate some random data, we send it to the software, and we see if it crashes. This is really the simplest approach that we can have. It's very easy to set up because we really don't need anything else apart from the software running, and a way of generating random data, but it's quite easy. The only problem is that we cannot really rely on this method to find a lot of bugs, because we can really just scratch the surface of the program. The other approach that is the most used nowadays is called the gray box approach. In this case, we must rely on some knowledge on the internal of the software, because at runtime we wanted to retrieve some feedback data from the execution of the program, and we want to rely on this feedback data to generate more relevant use cases. This is really the most used approach. There are a lot of tools that helps with that. Some of them we will be using it today. I've been using them for fuzzing and ntopng, like LibFuzzer and AFL++. Those are very well-known tools for these kind of things. The last approach is the white box fuzzing. In this case, we rely on the full semantic of the program. So that means that we don't have to rely on brute forcing too much the input. We just can, starting from some constraints, we can generate an input that solves all those constraints. And this is really cool, really interesting. The problem is that it's very hard to implement, because it's very hard to retrieve the semantic of an instruction, and semantic of problem is even harder, and even when you do, it's very slow, because you usually have to symbolically execute software. It's very hard and very slow. And there are not a lot of tools that help you with that. One of them is Fuzzing, that is a collaborative fuzzing engine with a Triton DSC that is a dynamic symbolic executor. But yes, for ntopng, I just focused on gray box fuzzing, and I used a coverage-based approach with an evolutionary algorithm for generating new inputs. What does it mean? Basically, we start the source code of ntopng. We want to compile it and instrument it with some code that will be executed at runtime, and that will generate the code coverage for that particular execution. So when we submit an input to ntopng, in this case we will see what the input will mean, will be represented. But in any case, when we send some kind of input, we know at runtime what is the code that is being executed, and we use that code coverage as a fitness function for generating new inputs in an evolutionary algorithm fashion. Just a word on source code instrumentation. This basically means that at compilation time, we want to add to the code some kind of information about the trace of the execution. It's basically what I said before. It's a way of measuring the code coverage. There are different ways, different metrics that we can use. We can use like how many instructions have been executed, or also like the path coverage. So if we execute a for loops 11 times, it's different than executing 10 times. In this case, there are all this instrumentation. We don't have to do it manually. Fortunately, we can just rely on some tools to do that. Using these tools, it's also very convenient, because most of the time those are just wrapper over compiler like GCC or Clang. In the case of Fuzzer, it's part of LLVM, so it's really just need to use a Clang to compile. So this was a brief introduction on how fuzzing generally works. Let's see how we will apply it to ntopng and how I apply it. So the idea is that first we want to identify a target in the source code that is meaningful to be fuzzed. It's usually a function that contains a lot of code that is not really, it might be complex, like and there might be a lot of memory allocations, so it's easy to introduce flags. In this case, parsers are usually a very good choice, because yeah, usually it's very hard to write with parser. After we identified an interesting function that we wanted to test, we want to isolate it from everything else, because we really want to execute it as many times as possible, because the more times we can test it, the more likely it is that we will find bugs. So we really want to focus on efficiency. That means decoupling that function from everything else, being able to execute it as reliable as possible. So we want that the same input generate the same execution every time, or at least that's the ideal way we want to have. After that, we wanted to generate an initial corpus. I said before that I'm going to use an evolutionary based mutational algorithm for generating new inputs. So the initial population is very important. We already start with a good test case, test set, then it's going to be more efficient. The whole fuzzing test will be way faster. It's sometimes tricky to find the good test cases, but it's really worth to spend some time generating them. At this point, we are almost done. We wanted to just generate the harness. That is the clean code that will make interact the fuzzing engine that we use with the software that we want to test. In this harness that we will have to code, we will put all the configuration, all the initialization of the software, everything. At this point, we are ready to fuzz, and in this case, we want to fuzz for as long as possible, since there is no real end of fuzzing every time we are generating new inputs. After a while, of course, we will start to not find anything relevant anymore. There is like an asymptote that we will reach at some point, but in general, we want to fuzz for as much time as possible. At this point, we will have all the fuzzer running. We would like to also integrate it in the CI so that everything will start automatically every time we push a commit to the repository, or every time we create a tag or whatever. So this is like the general overview. Let's see how we apply it to ntopng. So let's start with the function identification. ntopng is a quite complex software. It's made up of several different parts. There's a C++ core. There's the HTTP server with Lua scripts. There are the Python bindings, and then there are all the other, let's say, external projects, but they are still part of the ecosystem, like NDPI for the deep packet inspection, and Edge, and Probe. There are a lot of stuff. So the attack surface is really wide. In this case, I decided to focus on the C++ core, as it's where most likely we can find bugs, because in C we have a lot of memory applications. It's really hard to prove that the code is really doesn't contain any bugs. So this is a general overview on how ntop internally works. This is really just a general overview. Don't rely on this too much, but it's useful to explain where our target will be. So when you start ntop, ntopng, under the hood you are creating an ntop object that will load all the configuration from command line or from files from a prefs object, and after that we load one or several network interfaces from which to load the traffic. And these network interfaces can be several different stuff. It can be a pickup file or just a regular interface. There is the ZMQ collector from collect packs from other interfaces. There are a lot of different ways. So as we can see from here, a good, interesting target to fuzz might be the prefs object, where we have the configuration file, because we will have a parser for the configuration options and everything, and it might contain some bugs. But the problem is that because in ntopng it was not that complex, that code, and in any case it's not really relevant from a security perspective, as the configuration usually is not something that is controlled by an attacker. It depends on the threat model, but in any case, for sure, we can focus more on the network interface, because that's where the traffic that is being analyzed by ntopng is coming from, and that traffic might be malicious. And that's exactly what I try to focus on. Internally, when you start ntop, you call the start function that will call the start packet polling for each network interface. In this case, I will just focus on the case where we only have one network interface to monitor, since the code is always the same. In this start packet polling function, a pool of threads will be initialized, and each thread will do a packet polling to the interface, and every time there is a new packet, then it gets analyzed. And when it is being analyzed, the function this packet will be called. That will be the one responsible for analyzing packet, which we call NDPI under the hood. So this is really an interesting target because it's where a lot of code, a lot of complex code is inside. We can look at the signature of the function, and we can see there are many parameters, but in reality there are not, because the first one is just an identifier that we can submit. We can specify that there is a boolean that tells if the packet is in an ingress packet or not. There is a center MAC that we can ignore for the time being. It's not really useful. It's not really important from the Fuzzing perspective. Then we have the header of the pickup. Structure, and then there is just a buffer of raw bytes that is the context of the packet, and then the other parameters are just used as output for the function. It's where ntop will store the information that extracted from the packet. There is the flow, source host, destination host, and stuff like that. So basically, what we need to provide as input to the function is just the header of the pickup packet and the raw bytes of the packet itself. And this is really an interesting target because it's a simple interface to it, and it's really meaningful. It's basically the core where we analyze the traffic. So we identified the target. Let's see how we can isolate it from the rest of ntop. And this was really where a lot of problems started to happen, because ntop was not meant to be run as a library. It was meant to be run as a standalone program. So at startup time, there are a lot of stuff that will be initialized. The thread pool will be launched. A lot of stuff will happen. On my laptop, when I test it, the initialization takes roughly 1 second. That is really not important in production, but when you want to fuzz it, you want to be as efficient as possible. And since you will have to create many processes and start them all over, having 1 second of overhead is too much. And on top of that, we don't want thread pools, because we want to be as reliable as possible. And this asynchronous ways of analyzing packets is not really what we want. And on top of that, ntop uses the Redis as a caching system as an external dependency, and it's also something that we wanted to be control from. We want to remove Redis entirely. So how can we solve all this problem? Well, basically we just patch the code. We just patch the code, but we don't want to affect it in production. We just want it for our fuzzing tests. So we will use this standard macro, and we will, if that macro is defined, then we will patch some part of the code. Otherwise, we will just leave them. This is a quite tedious job, because you have to really find everything, and then you have to patch everything out, and then there are some problems, and then you have to also patch those problems, but it's the only way. We really want to just initialize the bare minimum components. For Redis, there was it was a bigger problem, because the code that was using Redis was really too much. We could, there are two solutions. We could patch every code to the Redis API, but in this case it was not feasible, as there were too many places where we were calling Redis. Or what I did was to create another class that was implementing the same interface of Redis, the same API calls, and then I swapped it to the official one. So I was basically creating a mock Redis that was not depending on the external servers, but was just handling everything inside the processing memory. Or sometimes just not doing anything at all. So it was quite simple after all. We just need to replace it. It was quite simple. Every time we had this include Redis page using the same macro as before, fuzzing with mode and save for production. We just, instead of including Redis page, include the Redis stub, that is my implementation. We just copied all the API from Redis page, and we just removed the implementation. We just recreated it. In the end, it was a very efficient way of decouplling from Redis, and it was way faster than patching every API code. So at this point, I had to create a corpus, an initial corpus. As I said before, having a good corpus is really meaningful, as the fuzzer will be able to find interesting new inputs sooner. So we really want to focus on a corpus that achieves already a good code coverage. And the idea is that we want to have some pickup traffic. We wanted to have some traffic in a pickup file, for example, that contains some invalid packets or something that looks like a bit malicious in some way, and that we wanted to trigger the edge cases on the top because we want to find bugs in there. So we really wanted to find the edge cases. Fortunately, I didn't have to spend too much time reinventing the wheel because I took it from the TCP dump test set that is already quite well done. It contains almost 700 pickup files of different sizes, ranging from 24 bytes to 500 kilobytes. And they contains a lot of invalid packets, some kind of attacks, something quite fishy, and it was already well done. So I just took it and used it for ntopng. So what about the harness? In the harness, as I said before, we just wanted to glue everything to the fuzzing engine that we'll be using, and the software itself. We want to initialize the state. We wanted to test the function dissect packet that we identified before, and after we tested it, we wanted to clean the state and start again all over. We don't want to have a persistent of a state across the execution, across different execution, because that means that we don't have the same reliability. We don't have the same execution multiple times. The only problem is that there are a lot of tools that we can use for as a fuzzing engine. The problem is that the interface to them is not always the same, unfortunately, because we would like to be able to use different ones without having to change the code. But in this case, I used the libfuzzer interface that is becoming a bit the standard one. It is compatible with libfuzzer and ntopng and some other fuzzer. And it's really simple to implement. Basically, there are two functions. The first one is LLVM fuzzer initialize, that is optional. We don't have to implement it, but it offers an initial function that where we can initialize all the objects. In this case, we will have to initialize the ntop object, the preference, the network interface, and everything. The other function that we have to implement, it's required, it's LLVM fuzzer test one input, and it has two parameters. the buffer containing some bytes. It's a pointer to unsigned char, so it's basically some bytes and the size of the buffer. And this will represent our test input that will be generated by the fuzzing engine. So at this point inside the LLVM fuzzer test input, we already have our generated input, and we just have to send it to the format it, send it to the dissect packet function that we want to test. Since this is part of the LLVM, it's also really easy to instrument a code that uses this interface. You just need to specify the fsanitize fuzzer flag plan. With the different fuzzing engines, it's a bit different, but with the fuzzer, it's really straightforward. So this was part of the code that I tuned up a little bit, and I removed some part, but just to give a general overview on how what I had to initialize inside the LLVM fuzzer initialize function. On the first row, we see that I'm creating the ntop object and the prefs object that contains the configuration. Then I'm setting some arguments to the ntop. Those are arguments that I had to specify. Then you register the reference. You have to initialize some internal data structures, and then you can create the network interface. This is just basically done. This is done only once per process. Every time you instantiate a new process, you execute this once, and this will initialize everything. After that, we have the real deal, the one where we want to test the function. We have our buffer, but if you remember, we have to specify the header of the pickup object, and then the raw bytes of the file. So in this case, I had to use the pickup functions to generate all the data structure needed for the function in the dissect packet. So I'm using fmm open, and I'm opening the file descriptor with all the pickup related functions. And after that, I'm iterating over all the packets, and each time I'm sending them to the dissect packet function, hoping to find a crash. That means there is a bug. Hoping. If there is a bug, it's better to know. At this point, everything is ready to fuzz. So I launched it with the lead fuzzer. This is basically what you see as an interface. Maybe it's a bit small, but on the left side you can see the coverage. That means how many instructions are executed by the particular point, because it executes all the corpus and then it tries to generate new inputs. And when it finds something new, it updates the corpus and adds that new input to it. You can see that the corpus size that is increasing, 366, 367, and the execution. In this case, the execution was a bit smooth. It was a bit slow. It was around 130 instructions per second. Usually, you want it to be around thousands, or if possible, tens of thousands of execution per second. But in any case, it was already good enough because we were generating a lot of code coverage. This is also the interface for AFL++. I had to write a different harness for this one, but because the interface changes a little bit. The interface in this case is a bit nicer. You have colors. And the execution in this case was also faster. You can see we are reaching 3,000 execution per second. And on the upper right corner, you can see we had saved times. That means that we reached a timeout. That indicates an infinite loop. That is already something that we want to get So this was really all the process of fuzzing. At this point, I wanted also to integrate it in the CI. And for doing this, there is a cool project that is OSS Fuzz. That is a Google-sponsored service infrastructure that lets you implement continuous fuzzing for open source software for free. If the project qualifies, it must be well known because the spots are limited, but in this case, they accepted ntopng. And in this case, we can rely on their infrastructure to continuous fuzzing ntopng. And each commit, we generate a new instance with the previous corpus that we generated that we build over time. So it's really interesting. It supports a lot of languages as well. You can even do Python fuzzing with different techniques, but it's really interesting. And there is also a reward program for interesting, for important contribution to OSS Fuzz. The only problem is that it took a little bit more effort to implement because everything must be automatized. While previously I had to compile everything manually, and I had to set up the environment manually. So it requires a little bit more effort, but it's really worth it because now we have continuous fuzzing integrated in the CI. So, as a conclusion, with this technique, we were able to find several bugs. I'm sorry that I was not able to show them, but we were able to fix them. It proves that fuzzing with this approach of coverage-based is really efficient, and it's not that hard to put in practice after all. It's easier for libraries. With the NDPI, it was a bit easier because because NDPI is already a library, it's easy to take Google from everything else. And also integrating with the OSS Fuzz was really meaningful, as we are now able to have continuous fuzzing without having to rely on somebody manually setting up everything. As a future work, we could improve our fuzzing harness, and instead of doing this evolutionary algorithm for generating new inputs, we can rely on structured fuzzing. An interesting project in this sense is libprotobuf mutator that uses the protobuf language to define structure for an input. And in this case, it's relevant because usually traffic is well structured. So we could do an even more efficient fuzzing campaign that might lead to new discoveries. And we can also try to fuzz other targets. I talked before about the configuration, but there are other targets like the Lua script engine that might be interesting. Yes. Well, that's basically it. That was my my journey on fuzzing and ntop.